Hi, I'm Chaymaa Boutahiri. Today I'm going to present the PID Control against LQR-Feedback Linearization control for a quadcopter. My presentation will be in 4 parts. In the first part we will discuss about the model dynamic of quadcopter. In the second part we will talk about the PID control, and in the third part we will present the LQR-Feedback Linearization control to conclude. A quadcopter is an unmanned air vehicle. At the extremity of the quadcopter, 4 rotors are placed. A force and a moment are applied to each rotor, which allows the movement of the drone. In this figure, we consider 2 frames: the body frame, which is related to the quadcopter, and the inertial frame, which is supposed to be Galilean. And to get the model dynamic of quadcopter, we consider these hypotheses. And before applying Newton-Euler mathematical model, we should have a rotational matrix R and the component of velocity P, Q, and R. Finally, we get the following equation: proportional integral derivative control. To achieve the right operation of the quadcopter, it's necessary to control the position, the altitude, the heading, and the attitude, and we consider a cascade loop. For the altitude, we have to act on the thrust force to obtain the control law of Z. The same for the attitude and the heading, we have to act on the couple U2, U3, and U4 as follows. And we get a control law of phi, theta, and psi. For the x and y position, we cannot control directly by the U command. However, we can control it through the rule and pitch angles, and we get the control law of x and y. Using MATLAB Simulink, we get the following results for the trajectory tracking, for the x trajectory, and for the y trajectory, and for the z trajectory, the same for the psi trajectory. LQR-Feedback Linearization control. Our unmanned air vehicle is a nonlinear dynamic system, multi-input, multi-output, written in the following form. The aim is to find the control law written in the following equation. By applying Lie derivative, we find the following equation. There is a relationship between the input and the output, as we see below. So, the nonlinear control law is written in the following form. Finally, we find a nonlinear transformation of Z. The objective of the Linear Quadratic Regulator control is to minimize a performance of criterion Chi. So first, we should find the matrix E and B of the system written in this form. Then we should choose the matrix Q and R to resolve the regulatory algorithm in order to calculate the gain. And we get the control law of U1, U2, and for U3, the same for U4. With V as new input. The same for the external loop, we consider theta equal to 0 and phi equal to 0 to simplify the result, and we get the following control of desired phi and desired theta with V1 as a new input. Finally, we apply the LQR control for the inner loop and the outer loop, and we have the following results. The same for the outer loop. Using MATLAB Simulink, we get the following result for the tracking trajectory, for the x trajectory, and for y trajectory, the same for z trajectory, also for psi trajectory. So we conclude that LQR-Feedback Linearization is more performant and more efficient than PID control. Thanks.